Bonjour à toutes et à tous et bienvenue chez moi. My name is Elizabeth Martin Jefremovas and I work as a postdoctoral researcher at the University of Cantabria in Spain. Today I'm going to share with you our work which is entitled Order and Disorder, the Magnetic and Crystalline Electric Field Skyline of Neodymium-copper-2 Nanoparticles. The outline of this presentation is going to be the following. First, I will briefly set the context and motivation of our research. Then I will also briefly explain the main experimental techniques related to this work, which of course are related to neutrons, and I will spend then most of the time of this presentation discussing the main results achieved in this study. The results have been split in two parts. On the one hand, we have evaluated the static magnetic structure by means of neutron diffraction and small angle neutron scattering. And on the other hand, we have evaluated the dynamic magnetic structure by means of inelastic neutron scattering. Then, of course, we will finish by citing the main conclusions of this work. In the last years, the study of the magnetic collective excitation have been meriting rising interest. The driving force beneath these studies is mainly the fact that antiferromagnets, especially antiferromagnets, have been selected as prominent candidates to be used for spintronic application and for spintronic devices. In the case of the nanoparticles, the way that these magnetic collective excitation are developed or are altered by the size reduction to the nanoscale have been mostly unheard, and the studies that can be found in this way are related to 3D phases, iron oxide phases. But there are almost no works reporting how this collective excitation takes place in, for instance, rare earth-based nanoparticles. There is only one work in 2017 published reporting how this collective excitation and crystalline electric field schemes are maintained in a quasi-crystal. But as I said, there are almost no reported works saying how this collective and single ion excitation take place in 4F-based nanoparticles. So we just wonder what happens to these 4F-based nanoparticles, and in our case, we have studied neodymium-copper-2. Previous evidence let's put this in context. Our previous evidence showed that rare earth-based nanoparticles, being binary alloys with copper, reveal the coexistence of antiferromagnet core, but the surface is in a spin glass phase, yielding to the super antiferromagnetic global state. Neodymium-copper-2, regarding neodymium-copper-2, we know that in bulk, this is a Kramer ions, meaning that the crystalline electric field splits the multiplets, giving rise to 5 doublets, the ground state level plus 5 excited levels. This is a previous work reported by Gratz and collaborators in 1991. Antiferromagnets, on the other hand, the core, as I said, in bulk, neodymium-copper-2 is an antiferromagnet with an L transition located at 6K, plus the existence of a reorientation temperature to an incommensurate phase at 4.5 Kelvin. In nanoparticles, what we are reporting is the existence of a surface spin glass-like phase. So, the two main questions that are going to be faced in this study are: how is this super antiferromagnetic nanoparticles, how is this super antiferromagnetic structure settled in the nanoparticles, meaning that does this reorientation still holds in nanoparticles or not? And on the other hand, how are the energy level schemes in the nanoparticles? I mean, how are these energy levels retained at the nanoparticles? So for this, as I said, we have produced the nanoparticles by means of a neck furnace, and then the nanoparticle size has been achieved by means of ball milling. And we have performed a first structural characterization by means of X-ray diffraction and magnetic measurements by means of discrete magnetometry. Concerning the neutron structure, of course, we need the use of large facilities, and we have performed the static magnetic structure has been evaluated by means of neutron diffraction at Laboratoire Léon Grijuin in Paris. Exactly. And the small angular neutron scattering has been evaluated by the use of zoom instrument at ICES in United Kingdom. And on the other hand, we have studied the inelastic neutron scattering at Institut Laoué-Langevin in Grenoble. So I will start with the microscopic structure, the neutron diffraction part. So the neutron diffraction performed in the paramagnetic region allow us to detect that we are dealing with nanoparticles of about 18 nanometers for 2 hours milled nanoparticles and 13 nanometers for 5 hours milled nanoparticle. We have also been able to observe the unit cell contraction with decreasing temperature. This decrease of the unit cell contraction is enhanced below the Néel transition, revealing the existence of a magnetoelastic effect in this alloy. But if we go now to the low temperature regime, where the where the antiferromagnetic state is well established, what we observe is that we observe these magnetic Bragg peaks, and this magnetic structure has been fed and is well accounted by means of a commensurate square-up modulation with two propagation vectors, the one connected to 0.600 and the third harmonic. If we go to the temperature region of between the between 0, of course, and between the reorientation temperature that took place at 4.5 Kelvin and the Néel transition, meaning that the incommensurate region, we do not observe that this magnetic state would be compatible with the incommensurate description that was held for the bulk alloy. So the nanoparticles do not account for this incommensurate transition, meaning that they keep the commensurate square-up modulation in the whole antiferromagnetic range. And we also observe the existence of a rise in the low Q, low angle region, indicating the existence of interparticle correlations. So to further understand or to further explore this interparticle correlation, we have performed small angle neutron scattering measurements. And what we observe is that whereas for the bulk alloy there is a clear peak near 3 nanometers -1, the nanoparticles do not account for this peak, meaning that this additional correlation felt by the magnetic moments of the bulk alloy is not retained at the nanoparticles. These interparticle correlations that were accounted by means of neutron diffraction are compatible with the existence of a surface spin glass-like phase that has been evaluated by time-dependent phenomena measurements. These time-dependent phenomena measurements reveal the existence of memory effects and aging phenomena that are understood in the field of spin glasses. Going now to the dynamic magnetic structure evaluated by means of inelastic neutron scattering, first I will set what is the starting situation. The starting situation, this is to say, the bulk alloy, has been studied in a previous study by Gratz and collaborators in 1991. They accounted for the existence of 4 peaks, P1 to P4, in the paramagnetic region, and then these peaks are shifted as the temperature is low down, meaning that there are some magnetoelastic effect, and below the Néel transition there is a magnum peak that has been resolved to be formed by 3 magnum modes in iron 6 measurements emerge. So, in our case, we have measured the nanoparticles and we observe that these 4 peaks are retained by the nanoparticles compared to the bulk situation. But what we observe, apart from the existence of this, of course, magnetoelastic effect, is a partial inhibition to the transition for the first excited level compared to the bulk situation. We also observe the existence of a magnum peak below the Néel transition. But in this study, we have decided to go one step beyond, and we have separated the contribution stemming from the nanoparticle core to the contribution stemming for the nanoparticle surface. To do so, we have assumed that our nanoparticles were formed by a core of about 9 nanometers and a surface of about 2 nanometers thickness, and we have subtract the nanoparticle core weight by the cell to core to nanoparticle ratio from the total inelastic neutron scattering. And what we observe is we obtain the INS, the inelastic neutron scattering stemming from the surface. And what we observe here is that these 4 peaks remain in the paramagnetic region, the 4 crystalline electric field peaks remain in the paramagnetic region, and here, what most important is that below the null transition, the magnum peak still remains. Going in a little bit more detailed description, we observe this partial inhibition of the transition to the first excited level, a softening of the crystalline electric field peaks, and what we observe is that this magnum mode, this peak associated to magnum, accounts for a positive shift, meaning that it is a shift towards greater energy values, larger energy values compared to the Bell situation. This is understood by means of the enhanced surface anisotropy, but also can be accounting for the stiffening of the RKKY exchange at the nanoparticle surface. So, the main conclusion of this work is that, on the one hand, neodymium cappuccino nanoparticles retain the commensurate bulk antiferromagnetic structure, but without the reorientation at 4.5 Kelvin. We account for a spin glass surface, and on the other hand, the crystalline electric field excitations are present in nanoparticles, but also at the nanoparticle surface. But as I said, in the nanoparticle surface, there is a partial inhibition to the transition to the first excited level, and also the collective magnum excitation are retained at the nanoparticles and also at the nanoparticle surface, where a stiffening of this magnum excitation has been accounted. So, if you want to learn a little bit more about this study, we have published very recently 2 articles, one connected to this static magnetic part and the other one connected to these collective magnetic excitations. The one connected to the static magnetic response has been published in 2022 in Scientific Reports, and the other one connected to the inelastic neutron scattering results has been published in Physical Review in 2021. So with this, I would like to say merci beaucoup pour votre attention, and I will be very pleased to, if we can get in touch one to each other. You can ask any question or any curiosity you may have by emailing to this email address or visiting my personal webpage, which is jefremovas.com. Thank you very much for your attention.